A set is a collection of objects. This definition is very loose, very vague, and usually that is why it might be difficult for students. It's just a collection of objects. We like to denote sets with capitalized letters, like a set A. And there are a few special sets. So for example, if you take the counting numbers 1, 2, 3, 4, and you never stop, this is just a list of numbers. But now we can make it a set by putting these curly braces around it. Now it's a set that we are giving by sort of listing its elements. Basically, we give the pattern and then the dot, dot, dot means don't stop. So this one, the set of all counting numbers, it's also called a set of all natural numbers. This set has a special symbol. You take the capitalized N and then you double this part. So this is a special set. So you can give a set by listing its element. Let's say that A is, let's say 1, 3, 5, 7. These numbers are what we call elements of the set A, and the notation is 1 is an element of A. So this reads 1 is an element of A. 1 belongs into the set A. So while we are at this notation, let's talk about B. Suppose B is 1, 1, 1, 3, 5, 5, 7. So the question is, when can we say that two sets are equal? And that's just a matter of agreement, a matter of definition. So that's not something that we can figure out with logic. Some people made this agreement, and probably there are logical arguments behind those agreements. So the question is, we have the same numbers in both sets. The difference is that in B there are repeated elements. So the question, are these two sets equal or not? And the answer is yes, these two sets are equal, which is why we only list things once. So if someone gives you this set, the first thing would be to sort of simplify and write it 1, 3, 5, 7. Unless you have good reasons, you should probably organize it increasing order. But this is not the only way to give a set. You can also say the set of... so here is another set. It's described with just using English language, the set of all letters in the English alphabet. So of course, we can translate that into the notation with the braces and we can list the letters. Let's call this set D. Two sets are equal if and only if they have exactly the same elements. So A equals to B. There are also sort of visual ways of giving a set. Here is a set S. So we just draw a circle and the stuff that belongs to the set that's inside the circle. So we could, this is yet another representation of the same set. So A equals to B and they both equal to S. You're going to see that in case of sets, a lot of the times diagrams will be helpful. You will see in set theory that there are lots of visual tools. There are all kinds of pictures that are helpful. And one specific type of a picture, which we will see, is called a Venn diagram. So P is a set containing 5 elements, the numbers 1, 2, 3, 4, and 5. Set Q would be, set of Q would be, say, the odd numbers between 1 and 10. And so a Venn diagram would look as follows. So most Venn diagrams come in a rectangle, not all but most, and the rectangle represents the universe within the context of the problem. So for example, when we say everything, that would have to be more specific. With me, you're going to see a whole lot the universal set, the first 10 positive integers. So that means that when we say everything in this problem, everything means all 10 of these. So this would be the universal set. So when we are done, the universal sets, all elements should be listed somewhere. So now I'm going to draw a bubble for P and another one for Q. And so now we have 4 regions. We have these floaters. A floater would be in the universal set, but neither in P or Q. One such number, how about 8? So 8 has to be in this outer floating part, because if we investigate P, 8 doesn't have it, Q doesn't have it, but U does. So somewhere it has to go. Actually 10 goes in there too, right? Because 10 is in neither set. So what could we put here? This is where we put stuff that is in P but not in Q. So For example, 2, right? 2 is in P, so we have to write it down somewhere inside this bubble. Well, it's either here or here. But if you put it here, like 1 goes here. Why? Because this is sort of the overlap. This is the set of all elements in both P and Q, right? And I should have much more space because 3 is in both and 5 is in both. So I run out of space there. Usually what we can do is go number by numbers. We're going to go by U. 1 is in both sets, so it goes in this overlap. 2 is only in P, not in Q, so it goes there. 3 is again in both. Then 4 is in P, but not in Q. 5 is in both. 6 is in neither, so it's a floater. It floats somewhere within the universe, but outside of P and outside of Q. 7 is, we put at least one number into all 4 possible regions, right? One region, it's in neither set, another one only in P, another one only in Q, and the 4th one in both. Okay, 7, 8, what about 9? 9 is only in Q. The way I check it is, let's first focus on U. Is everyone here? So 1, 2, 3, there is 4. There is 4, 5, 6, 7, 8, 9, 10. So we're good with U. Then, if we look at P, if we now ignore the bubble representing Q and just look at this, inside this circle should be all elements of P. Is there? 1, 2, 3, 4, 5. So we're good with P. And in Q, inside this circle, all we should see is 1, 3, 5, 7, and 9. 1, 3, 5, 7, and 9. So this is a correct Venn diagram. And it's going to be quite surprising how useful Venn diagrams turn out to be. They will be quite a powerful problem-solving tool. Let's see a new definition. Okay, so suppose we have these two sets, S and T. And I think it was time that I showed you that numbers don't have monopoly over who can be an element of a set. You can put anything into a set. We can declare the set of all people in this room, or the set of all cell phones in the world. We can put sets into sets. We can say here's set X, and we can put sets in there, A, B, and we can put a number or a letter in there. So it's really, really relaxed. So going back, it's kind of strange, but S has just 3 elements, 1, 3, and 5, and then T has much more. Now, this is not going to be a Venn diagram, but it is possible to draw a picture of T that includes S. So it would be 1A. The set S is 1, 3, and 5. The set T is 1A, 2B, 3C, 5D. So this is a correct graphical representation of these two sets. Now, notice that this is different from a Venn diagram because these two circles look like have a very different relationship. One is completely inside another. Indeed, anything that's in S is also in T, which is why drawing this picture was possible at all. And when that happens, we say that the one set is a subset of the other. So in this case, we can say that this is going to be the notation for S is a subset of T. This reminds me of the inequality. It's like when we smooth out an inequality symbol, and that bar here has the same function as in case of inequalities. And it also tells you who is quote-unquote small, right? S is smaller. Therefore, you can read this, S is a subset of T. One special set was the set of all natural numbers, or counting numbers. See, writing it down, set of all natural numbers, is a whole lot of work. So is this, which is why we have this compact little symbol. Kind of makes writing easier. So what set do we get when we throw in 0 and the opposite of all these numbers? So this is what we call the set of all integers. These are integers. So with these special sets, we always double something. Natural starts with an N, integer starts with an I. Somehow it didn't feel like it was a good idea to double capital I, because that might look like Roman numeral 2. It was just weird. So we probably wanted to go for the first letter of the word numbers, but that was already taken. So what happened is we took the German word for number, which so happens is Zahl, and because of that, the set of all integers is denoted by a capital Z, where you double this slanted part of the letter. So to practice some relations here, completely officially this reads 2 is an element of the set of all natural numbers. But that's the same as to say 2 is a natural number. See, this is how we quickly, without much writing, we say that 2 is a natural number. -3 is not a natural number. When we want to say not an element, we do what we do with equal. So this is not an element. So we can read -3 is not an element of the set of all natural numbers, or shorter, -3 is not a natural number. But both of them are an integer, right? 2 is an integer, and so is -3. So where I'm going is the fact that the set of all natural numbers is a subset of the set of all integers, right? Because we could draw a picture for the integers that would completely contain the other set, right? We would say, okay, let's have 0 here, and then 1 would go here, -1 again outside, 2 would go inside, -2 outside. There is a pattern here, right? 3, -3. So in this little circle, these are the set of all natural numbers, 1, 2, 3, and so on, right? So it's sort of completely contained. So the symbol reminds me of the inequality symbol, and whoever is the subset is at the smaller part. But I was hesitant to use the word smaller because these are two huge sets, right? It's not that trivial to compare them. They're both infinite sets. So it's the one contained that is on this part. If we draw a Venn diagram, well, we would have to first state what the universe is. But if we drew a Venn diagram about these two sets, see, a Venn diagram usually allows for all possible regions. This doesn't. So we would have to state what the universal set is. It's not that trivial. But if we call this the set of all natural numbers and we call this the set of all integers, 0 would go here because 0 is an integer but not a natural number. Then 1 would go here because 1 is both. It's a natural number and it's an integer. -1 would again go here, and then 2 would go in the overlap because it's both an integer and a natural number, and then -2 would go here. And then you can see this is what it will look like, that n is a subset of z, that this area will be empty, that everything that is in the set of natural numbers is automatically also in the set of all integers. That's subset. So let me write down the definition. So A is a subset of B if, and only if, for any element in A, it is also in B. The concept of subset, it's not that new. For example, how about this statement? So every cat is a pet, but not every pet is a cat. That is the classic case of subset, right? The set of all cats, let's say K, I'm looking for letters we haven't used yet. K would be the set of all cats. We can just write it down, then we don't need the braces. The braces are needed when we're listing things. And let W be the set of all pets. Then K is a subset of W. The set of all cats is a subset of the set of all pets. And that's the same as every cat is a pet, but not every pet is a cat. Right? Because, well, you can have dogs and birds for a pet. It's not all cats. There is another notation where you use these curly braces, but then you say X, and then you either see a vertical bar or a column, and we described what X has to do to be in this set. So we could say it's a positive integer less than 10, that's odd. So, see, that's another way of describing sets. Now, we have seen some strange sets, like the universal set is a little bit unusual. We also need a set that will behave similarly to as 0 behaves within the numbers. And so there is just one set that has nothing in it. It's called the empty set, and it has two notations. I think this is the official one, but ever since my open math prefers just this. So we just enter, so this is on the internet, we just enter a pair of curly braces with nothing in it. Don't do both, because I told you you can put sets into set. This is a one element set, and the only one element within this set is the empty set. Sort of like double bagging something. The outer bag has something in it, right? The inner bag. Okay. So we have introduced the idea of a set when two sets are equal. What does it mean to be an element of a set or not being an element of a set? What does it mean when a set is a subset of another set? And then we learned all kinds of notations. This is a special set. It has its own name. This is the set of all natural numbers. This is the set of all integers. And then we also looked at Venn diagrams. But Venn diagrams most of the time come with this strange set, the universal set. For example, from geometry, you can have the universal set to be the set of all points in the xy plane. And then everything that we discuss is going to be contained within the universal set. And then we have seen another special set, the empty set. So this is going to be strange, but the empty set is a subset of any other set, including itself. Now if we go back to the definition, what does it mean to be a subset? A is a subset of B if for all x in A, x is also in B. So this statement would be true if for any element of the empty set, it is also in A. There is no element in the empty set. This is what we say vacuously true. Let me give you an example. Suppose 20 people get together in a room and they sit down, and turns out that none of them has a cell phone on them. So the room has no cell phones in it. Then the following statement is true, strangely, but true. Every cell phone in the room is turned off. That's a true statement. Also, every cell phone in the room is turned on is also a true statement. And sort of similarly, for every set A is a subset of the universal set. That's sort of by definition, because U has to be everything within the context of the problem. And by the way, A is a subset of itself for any set A, right? Because everything that's in A, well, that's also in A. Let's practice a little more. Let R be the set of all rectangles and S be the set of all squares. Now, this is a little bit unfair because we didn't define these things. So a rectangle is a four-sided polygon or quadrilateral with four right angles. So the definition of a rectangle is that it has four right angles. Now a square, what's a square? Even the phrasing is going to give away what the relationship between these two sets is, because a square is a special case of a rectangle, right? A square has four right angles, therefore by this definition it is a rectangle, right? But also two neighboring sides are equally long, right? And that will actually force that the opposite sides are equally long, because that's true already for the rectangles, right? The opposite sides of a rectangle are equally long. So a square is a special case of a rectangle. So right here, the set of all squares is a subset of the set of all rectangles. So a square is a rectangle with four equal sides. So that subset, that is the same to say that every square is a rectangle, but not every rectangle is a square. So that's classic case of subsets. Every square is a rectangle, but not every rectangle is a square. So we have many examples of that all over the place. Now, how did we define? By the way, the definition is a matter of agreement. You can never know a definition because you're smart and you figured it out. Definitions are agreements. Basically, we have to agree before we start discussing something what we mean by what. So what do we mean by a square? A square is a rectangle with four equal sides. But then someone could say, okay, well, what's a rectangle? And then we can say, well, a rectangle is a four-sided polygon with four right angles. But then someone could say, okay, what's a polygon, right? And a polygon is when in the plane we have a bunch of points and we connect them with straight line segments. That's a polygon. Poly means many in Greek, right? You might have heard the word polynomial. So polygon. So where are we going with this? Definitions are sort of interesting because definitions will refer to something we already know and specify. What's a square? Well, a square is a special case of a rectangle. What's a rectangle? Well, a rectangle is a special case of a polygon. And then we could say, what's a polygon? And we can describe it as I did, that points on the plane connected with straight line segments. But then we could ask, okay, what are line segments? And the more fundamental we reach, the more difficult these definitions are. But logically, there is some sort of a hopelessness here, because if a definition works like we grab something we already know and specify, then our first definition is in trouble. We don't know anything, so then we cannot grab a part of it and specify it. And so it is in the nature of definition that there will be at least one thing that we don't really define, we just assume that everyone understands, that there has to be a sort of the first definition. And the first definition in mathematics is the concept of a set. Everything that you have seen in mathematics until now have been sets. For example, what's a circle? A circle is... So what's a circle? How do we define a circle? If we have a fixed point and have a fixed distance, then the set of all points, that distance away from this point. Well, actually, this is not a circle yet because we didn't say in the plane. Imagine a point somewhere here, like the end of my finger. And now, where are all the points exactly 1 foot away from that? Or 1 inch away from that? What would you see? I'll let you think about it, but for now, if we add in the plane, then we get a circle. So what is a circle? The circle is the set of all points in the plane equidistant to a point. That fixed point is the center of the circle, and that equal distance is what we call the radius of the circle. So I just wanted to mention, because I find it interesting, that the most fundamental concept in mathematics, upon which everything else builds, is set, is the definition of the set. So sometimes you will hear mathematicians say that, you know, the saying a rose is a rose is a rose. Sometimes you hear a set is a set is a set. And then everything we defined after are sets. So pretty much every even the numbers are sets too, the way they were thoroughly defined. Thank you for watching.